Welcome back. In today's lesson, we're going to discuss the topic of solving polynomial equations. Recall that at the beginning of our discussion into polynomial equations, we talked about how factorization is a technique that can help us simplify what are known as rational expressions. And a rational expression is any type of expression that exists in mathematics where you have a polynomial in your numerator divided by some sort of a polynomial in your denominator. And these are nasty equations that pop up over and over and over again in the engineering and physical sciences, as well as chemistry and a number of other places. And so it behooves one to know how to deal with situations where you may have a polynomial divided by another polynomial. In this instance, if we were to say use the GCF technique, we could factor the polynomial in our numerator by pulling out 2x, which would be the GCF of 4x squared plus 2x, and we would have 2x plus 1 remaining. Now in our denominator, we may be able to pull out a 3x, and we would have a 3x plus 1 remaining. And by doing this procedure, you would then be able to cancel like terms in a similar manner as canceling the like terms of a ordinary fraction. So in this instance, you have an x on top and an x on bottom, so you could cancel those x's out. We'll talk more about how to deal with rational expressions when we get to chapter 10. But today's lesson is a more useful way to utilize the tool set of polynomial factorization, and that is whenever you're actually tasked with solving a polynomial expression. Consider the difficulty of actually determining what x value needs to be plugged into this equation such that the expression 9x squared plus 3x would in fact multiply together and add up to equal 0. This is in fact not an easy task because if we try to use the guess and check method, I hope everybody would agree that we may be spending a very long time just guessing different x values that we could try to plug into this expression. I could, for example, guess that x might equal -1. And if I were to plug it into this expression, it's not entirely clear that I would be able to, in a reasonable amount of time, just guess at which value might cause this sum to equal 0. In this instance, we should see that 6 is equal to 0, and of course that's nonsense. That implies that our choice is incorrect, and we need to try again. But we could sit here for hours and hours and hours and never guess the correct x value. So the question is, what are we going to do? And it turns out that in algebra, all we need to know is what is called the zero law of algebra. The zero law of algebra may seem obvious to many. In fact, it may seem so obvious that it doesn't even need to be mentioned. However, the use, like many of our other rules of algebra, the use case for the zero law of algebra is not in fact very obvious. So the zero law of algebra says that anytime you have two numbers and they're multiplied together and happen to equal 0, then either A must equal 0, in which case you have 0 times B gives you 0. B could equal 0, in which case you have 0 times some number A, and anything times 0 gives you 0. Or both A and B could be equal to 0, in which instance you would have 0 times 0, which would indeed give you 0. Now, how this is important or where this is going to be used is if you have an expression, an equation such as 9x squared plus 3x, and this is in fact equal to 0, and you were able to factor this expression, say by using the GCF technique, then what happens here is you actually have a situation where A times B will equal 0. And while we're not used to thinking of the term 3 times x as being just some number, because we actually don't know what x happens to be, if we did know what x was, if x was, say, 1, then we would just have this have some value, 3 times 1, right? And while we're not used to thinking of an entire equation, such as 3x plus 1, as being just a single value, if we did know what x happened to be, we would take our x value, we would be able to multiply by 3, add it with 1, and of course that would give us just some number. And so indeed 3 times x and 3x plus 1, they are just numbers, and because that's the case, when they're multiplied together and they're set equal to 0, that means that the first value, this a, this 3 times x, that could be equal to 0, or possibly the 3x plus 1 is equal to 0, or they're both equal to 0. In either case, if you then solve for x, you get x must be equal to 0. We also get 3x is equal to negative 1. So x is equal to negative 1/3. Okay, and this often confuses students, but you will in fact have two solutions. For a polynomial of degree 2, you will have two solutions. If you have a polynomial of degree 3, you'll have 3 solutions. If you have a polynomial of degree 4, you'll have 4 solutions, so on and so forth. So if you are dealing with a polynomial expression where the leading exponent is raised to the second power, you will always, in fact, have 2 independent, individual solutions. Not necessarily independent, meaning that you could, in fact, have repeating solutions, but they will be 2 solutions as opposed to just 1 solution. Okay, let's see a more involved example. Suppose you've got something like x squared plus 9x plus 20 is equal to 0. And the question asks you to solve for x. What are we going to do? Okay. In this instance, go through your checklist process. We're going to check first to see if you may factor the polynomial expression using a GCF. In this instance, we're not going to use a GCF because on the one hand, there really isn't a leading term for our x squared value, but then also we're dealing with a trinomial expression. So in general, for trinomials, you're not necessarily guaranteed to be able to use a GCF. In only a few instances, specifically instances where there is in fact a leading term in front of your x squared, that might be a case where you could potentially factor using the GCF method first. But in any other case, you're either going to use guess and check, or you're going to use the factor by grouping technique or the extended, guess and check method in order to try to factor the trinomial expression. So in this instance, probably guess and check is going to work the best. And we know from chapter 6.2, 6.3 that to do guess and check, we just factor the last term. 20 is going to be the same thing as 5 and 4. 20 and 1, 10 times 2. That's going to all multiply together to give us 20. And so now all we have to do is we check to see which of these factors adds to the middle term. In this instance, the term 9. And so we ask, does 5 plus 4 equal 9? Does 20 plus 1 equal 9? Does 10 plus 2 equal to 9? And of course, 20 plus 1 and 10 plus 2 don't fit the bill, but 5 plus 4 does in fact equal to 9. And so our conclusion is that the factors must be x plus 5 times the quantity x plus 4. And this means that x plus 5 is equal to 0. Or x is equal to negative 5, but it also means that x plus 4 is equal to 0. Or x is equal to negative 4. Let's try another slightly more challenging example. Suppose we now have a leading term. this instance 2x squared plus 5x minus 3 is equal to 0. Because we have a leading term, this time for our trinomial expression, we will probably use the factor by grouping method or the extended guess and check method. Now, I obviously advocate for using the factor by grouping method because I just think it works a little bit nicer or a little bit more nicely. So we're going to take the last term, in this instance -3, we'll multiply it by the first term, in this instance 2, and we're going to get -6. And what we do with this -6 is we need to figure out what terms can multiply together to get -6, but also add to be the middle term 5. And so obviously, -6 and 1 would multiply to get -6, but -6 and 1 would, of course, add to -5. But if you did, say, a -1 and a +6, that would be the winner-winner chicken dinner. And of course, you would have to try 3 and a -2, as well as a -3 and a +2. So all of these could be possibilities, but ultimately, -1 plus 6 would add to be -5. And so while the other possibilities we would have to check through, we would be able to say that we may expand this expression 2x squared plus 5x minus 3 to the new expression 2x squared minus x, or 1x if you want to, plus 6x minus 3 is equal to 0. Okay? That's from the guess and check method. So come into my office hours if you don't remember how to do this. Otherwise, you're going to be very, very lost in this chapter. Now, for the not the guess and check method, but for factor by grouping, rather, you're going to want to find all the prime factors of each of your terms, which of course is not too bad since we've done it so much now. You'll see we've got an x term and an x term, a 3 and a 3. So let's go ahead and factor those terms out. I get a 2x minus 1, and I get a 3 times 2x minus 1 again. That's an indication that we're on the right track. We'll factor out the 2x minus 1, and we'll be left with the x plus 3 terms remaining. Everything, of course, equal to 0. And so from this point onwards, we're one step away from our answer. We set everything to 0. I'm going to set x plus 3 equal to 0. I'm going to set 2x minus 1 equal to 0. Of course, I need to add a 1 on both sides. Gives me 2x is equal to 1. And we'll divide by 2. That's going to give me x is equal to 1/2. Here, I'm going to subtract 3 on both sides. And I'm going to get x is equal to -3. Fantastic. One final example. Again, in many instances, what the textbook is going to try to do is it's going to try to take what we think we know and it will extend it a step farther. So suppose they gave you the following equation and they say solve for k, and then for the equation that they give you 4k squared plus 9 is equal to -12. Okay, all right. So what are we going to do? In situations where you've got variables on both sides of your equal sign, you're going to need to choose which side you want to work with. Now, my recommendation would be to pick the side that has your k squared term on it and work on that side. Okay, so if the left side has your k squared term or your highest degree term, that's going to be the side I want to work on. And so in this instance, because my k squared is on the left side of my equal sign, I'm going to go ahead and I'm going to add 12k to both sides of my equation. And I'm going to get 4k squared plus 12k plus 9 is equal to 0. Here again, because we have a leading term for our trinomial, we're going to use the factor by grouping method. We're going to take the first and the last terms, we'll multiply those together. 9 times 4 gives me 36. And then I need to see which of these factors of 36 will, of course, add to my middle term, 12. Of course, 6 and 6 gives me 36. 36 and 1 gives me 36. 12 and 3 gives me 36. And 15 and 3 gives me 39. Is there anything I can do here? I believe 3 does divide 36, but that would give me 12. So 18 and 2 gives me 36. There we are. So those should be all the factors of 36, if I'm not mistaken. So, all right, you're going to check to see which of these adds to the middle term. 12, go down your list. And of course, none of the bottom 3 work, but 6 plus 6 does indeed equal 12. And so what you can say is that 4k squared plus 12k plus 9 may be expanded to 4k squared plus 6k plus 6k plus 9. All of this, of course, equal to 0. And at each step, you need to be bringing down all of your terms, guys. If your equation said equal to 0, that needs to stay the same when you go from one line to the other. And if I don't see that on your exam, it's going to be some points missing, okay? And I don't want to have to take off for petty stuff like that, but look, it's the only way to keep students accounting for their operations, okay? I do have to penalize people just as a negative incentive. Now, at this point, the factor by grouping says that we need to find sets that are in common. Of course, I have a 3 and a 3 in common. I've got a 2, a k, and a k in common. So now I'm going to factor out the common term. And I write what I have left over. So I've got a 2k, I've got a 3, I've got another 2k, and I've got a 3. Of course, everything looks good. You're going to have a 2k plus 3 times, in this instance, 2k plus 3. Or, this is actually the more ideal scenario. It looks like you've got 2k plus 3 is quantity squared is equal to 0. And in this instance, that would just allow me to have 2k plus 3 equal to 0, because I don't even necessarily have to set each of the factors equal to 0. I can just take the square root of both sides. And if I take the square root of both sides, that clears the exponent, leaving me 2k plus 3. And of course, this is a two-step LEOV. So we're going to start by subtracting 3 on both sides, and then we'll divide by 2. Our solution is thus k is equal to negative 3 over 2. And of course, that's what you would get if you took any of these individual factors. You would take 2k plus 3 equals 0. And then you get 2k is equal to negative 3. K is equal to negative 3 halves. Watch out for any instance where you can just take the square root of both sides and then solve a much simpler problem. Sometimes that's all it takes is an ability to recognize what situation you might be dealing with at a given moment. With that, guys, I'm going to let you go. Take care, and I'll see you in class.